And we'll go from current slide, which I forgot to do too, but now we will. And to begin with, we will find some white space. There's a good looking bit of white space. But before we go there, just hit a few issues, nothing too major, except again reminding you here, one of my best classes of all time, and I have 5 papers in. Better than some classes, but still more than halfway through the term and don't quite have all the papers in. First test, we're still missing 1, 2. When I can get those 2 in, I can return those to you. I'd love to get rid of them. And I think I just got the second test 2 in, so beginning to get those. And we're moving along in chapter 5. All right. I don't think this will bother anybody, but there is a faculty meeting Thursday afternoon. I don't remember what time, sometime around 2 or so. But they told us not to cancel classes, so it shouldn't affect you any. If you have a class on Thursday afternoon, you probably will still have the class. But you might want to check with the instructor just in case for some reason that instructor has to be at the faculty meeting. If they do, then you may be missing a class then, but it shouldn't be. I'm teaching my class, so it doesn't matter. Okay. Next, then, on Friday, normally I have office hours on the Birmingham West Campus from 8 to noon. However, this Friday I have an eye appointment right across the street here at the UAB West Hospital. I thought it would be at Eye Foundation Hospital, but he's here tomorrow, so I'm going to have that appointment tomorrow at 8:15. So hopefully I'll be back to Birmingham sometime around 10 or so, plus or minus from 10 o'clock. I don't know how long the appointment will take, hopefully not too long. And it's just a routine exam. I have a feeling my second cataract is getting, they've already replaced one. I think it's getting a little worse because I'm having more eye strain. So they aren't going to do anything except hopefully discover whether I need to do something. They'll set me up an appointment later, but that's the main reason I'm going in. So anyway, that's Friday. So don't look for me before 10 o'clock. I may not be there by 10, but don't look for me before 10. All right. And I still haven't heard if they've announced about midterm progress reports. If they have, then the only people that are in any real danger are those 2 people who haven't turned in either a paper or the first test. Those have to give an alphabet midterm. Not that it really matters any, just you may start getting bugged about, do you need counseling, do you need tutoring, do you need help, this kind of stuff. So to avoid that, please get your work in. All right. Any questions from you? Math, administrative, otherwise? All right. Then let's go with example 9 at the bottom of page 352. It's the last example in section 5.1. Then we'll move on to 5.2. All right. Here's what it's asking us to do, if I can get my pen altered here. Okay. Rewrite this. The natural log of absolute value cosecant theta plus the natural log of absolute value tangent theta as a single logarithm and simplify the results. All right, now this is calling on you to retrieve in your mind what some of the principles or rules of logarithms are. Does anyone remember? Okay, here's Caitlin and Bree. All right, we're doing the last example, example 9 in section 5.1, and this is on page 352. Does anyone remember what it means to add two logs together. What's that the same as? It'll still be a log, but it's going to be a log of something else. Anyone remember that principle?
It's the log of the two things multiplied.
Okay, yes. That's what logarithms do. Number one, they take really big or really small numbers and fit them into a range that's much more usable, okay, because you're dealing with exponents of them. So a really big number like 93 million, which is the distance from here to the sun on average, miles anyway, that would be 9.3 times 10 to the 7th. So basically, that would turn out to be a number like 7 point something. So you take a really big number and scale it down to something much smaller. Or a really small number like Avogadro's number, 6.023 times 10 to the minus 23. No, that's a positive number, positive 23. Just anything like a micron is 10 to the minus 6 millimeters, meters. Okay? Well, that would be a number around minus 6. Okay? So rather than 0.00001, it would be negative 6. Okay? So it takes really split. Okay. So that's one thing it does for you. The other thing it does for you is make multiplication, division, and raising power simpler because it basically steps things down a level. If you've got two numbers you're multiplying together, you can take the log of the product, and that's the sum of the logs. Exactly the opposite of what you said. The sum of two logs is the log of the product. I bet you, maybe if you're really into history and stuff, you might remember what a slide rule is. Anyone have a concept? You ever see one? No. Okay, you've heard about them from the old fogies, you know, okay. That's when I was in college, there were no calculators. The first calculator I ever saw was my sophomore year in college. I was in a physics classroom, 8 o'clock in the morning, I believe it was anyway. Here's Jemiah. And first quarter of my sophomore year, and in walk, it's like a 200-seat room, and there it was filling up. 8 o'clock, it filled up slowly, but it was filling up. And then in walked these two guys. They worked together, but separately. You know, both of them had one of those big old calculators strapped to the belts. We'd all heard about calculators, but we went a collective, oh no, there goes the curve. Because calculators, all the rest of us had slide rules, you know, that we hauled around with us to do tests and things. Because that's how you could do, you enter and the slide rule is on a log scale, everything's on a log scale. You enter the first number, slide it over to that number on the lower scale, then take the window and slide that over to the upper number on this scale, and you add those two logarithms together, and then you take the anti-log, or you reverse the process, and there was your answer. That's how you multiplied really big numbers, and dividing was reversed, and raising to a power, it was multiplying two numbers. So you could do that kind of stuff. You could add or subtract on a slide rule, but you could multiply, divide, and those are the more complicated operations. So but there goes the curve. Now the reason the rest of us didn't have them, those calculators could, I mean this is really special, they could add, they could subtract, they could multiply, they could divide. Okay? And they cost about $400. And I couldn't afford that, you know, not when I was in college. And the rest of them, oh no, there goes the curve. Now, and the other thing, you had to plug them into the wall. They didn't have, it was a different world back then, folks. But before I got out of college, everybody had calculators because the prices had plummeted, you know, stuff like that. But it's still. So you're absolutely right. This is the log of the product. So this will be the log of, and we'll put it all in one, cosecant theta, I can't write, times, I said I was going to put them in, but it's easier to put them like this, tangent theta. Okay. Now, where would you go from there? That is, you have done the first part of it, rewrite that as a single logarithm. Yeah, there it is. but it says simplify. How can we simplify this? I think I will put them all inside one absolute value sign here. Second? Very good. If nothing else, get them all in terms of sines and cosine. 1 over sine theta. And what is tangent theta? Sine over cosine theta. So this will be, the sines go out, and that gives you the log of 1 over cosine theta. And you probably still should put it, or at least the cosine, in absolute values. But what is 1 over cosine? That's the log of secant theta. Now, depending on where your theta is, you could lose or not lose your absolute value bars. Why do you have to put absolute value bars around them anyway?
Can't you not have it be negative?
You cannot take the log of either 0 or any negative number, ever. Log is not defined for anything but positive values, not even 0. Not defined for 0, not defined for negative. That's why you have to put absolute value sets to keep that from being negative. Now, I won't go any further. All right, and that is exactly what we got in the book. And there is a checkpoint there. Please do the checkpoints as soon as you can. We didn't do the vocabulary, did we? Okay, let's do vocabulary quickly. Fill in the blank to complete the trigonometric identity. What is sine u over cosine u? Just did it. Sine u over cosine u. Tangent u. 1 over sine u. Just did that one too. Second, cosecant u. Okay, what is 1 over tangent u? Cotangent u. What is secant of pi halves minus u? Cosecant u. What is sine squared u plus cosine squared u? 1. And what is sine of minus u? Minus sine u. Perfect. Sine is an odd function. Homework exercises here would include any of the odds of 7 through 11. They're all at Calc Chat. 7's at Calc View. Any of the odds 13 to 17, they're all at Calc Chat. Do either 19 or 21 or both. They're both at Calc Chat. 19's at Calc View. Do any of the odds 23 to 31, they're all at Calc Chat. 25's at Calc View. Do any of the odds 33 to 39, they're all at Calc Chat. 35's at Calc View. Do 41, it's at Calc Chat. Do any of the odds 43 to 47, they're all at Calc Chat. 43's at Calc View. Do 49, it's at Calc Chat. Do 51, it's at Calc Chat. Either 53 or 55, they're both at Calc Chat. 53's at Calc View. Do 57, it's at Calc Chat, and 59 is at Calc Chat. Either 61 or 63, they're both at Calc Chat. 61's at Calc View. Then there's a applied problem 65, that should be at Calc Chat. There's a true-false at 67, that should be at Calc Chat. There's a do 69, it should be at Calc Chat. Now 71, I really don't like these too much. I know the reason for doing them, but they're trying to get you to find the error. I just hate for the book to write an error in it, okay? It's just, I'd rather not see errors in book, but they put a big red X saying they know it's wrong, you find out what's wrong. So that's 71, or you can not do it, whatever you want to. 73 you should be able to do, and 75, they're both at Calc Chat. All right, any questions on any of that? So I'm going to go on and delete. Anyone need this one up a little longer? Okay. So let's go back. We're still in Chapter 5, Analytic Trigonometry. We're analyzing things with trigonometry. And 5.2 is verifying trigonometric identities. Okay, now this is a part that typically people either enjoy doing them or they absolutely hate them. Okay, but they're sort of fun in my mind, but you know, they can be tedious. Okay, now our objective, to verify trigonometric identities, which is the title of the whole section. Okay? And we'll introduce it with this. In this section, you'll study techniques for verifying trigonometric identities. But before we do that, just get in your mind, these things look identical, and they're not always. Remember, most of what we've done in algebra and trig and just about anything in math, we deal with what we call conditional equations. Especially if you have a variable involved, it's a conditional equation. What that means is it's true for only some values in the domain. For instance, sine x equals 0. Is that true for any value x? No. Okay? Because it's only true at x equals 0, pi, 2 pi, 3 pi, 4 pi, minus 5, minus all of your n pi's. That's the only values. That's a conditional equation. It's not always true. Sine does this. Sometimes it's 0, sometimes it's not. Most of the time it's not 0. Okay? It's only true when x is equal to one of your n pi's. Now, linear equations usually have one solution. Quadratic could have two. This one has infinite numbers. Okay? N is an infinite. Those are conditional equations. They look just like what we're going to be dealing with, but they're not the same. On the other hand, whichever hand you started with, the other hand, an equation that is true for all real values in the domain of the variable, that's called an identity. We've already hit some. Sine squared theta plus cosine squared theta is equal to 1, no matter what angle theta you put in there. It's always true, okay? And this is just that same equation written in a different way. Sine squared theta is equal to 1 minus cosine squared theta. You cannot put an x in there that will make that untrue. That's true for every. It looks just like an equation, but equations are most of the time conditional equations. This is not conditional. That's an identity. That's true for all real numbers x, so this is an identity. In this section, we're going to be dealing with identities, not equations. So all the rules that we used to have for solving equations, don't use them here. Some of them is okay, but be very careful when don't get into the habit, oh, I'm trying to solve this. No, you're not. You're trying to show it is an identity. Verify that it's an identity. Although there's some similarities, verifying that a trigonometric equation is an identity is quite different from solving an equation. Okay? No well-defined set of rules to follow. It's best to learn the process by practice. Now, they're going to give you some guidelines, but let me give you one hint. In solving an equation, what is it we quite often do? We add or subtract or multiply or divide, the same thing on both sides of the equation. Do not do that here. Do not ever cross the equal sign. Deal with stuff on this side, deal with stuff on that side, but don't move things from one side to another. Ever. You're verifying the identity. You're not wanting to change the identity. You're verifying. And when you move things around, you're changing your equations. Okay, so that's the one thing. Now, what can we do? Well, we can factor. That's fine, as long as you stay on one side or the other. And you can do both sides, yeah. You can combine like terms. You can do whatever you want to on one side and do it to the other, but don't do the same thing to both sides. Don't ever cross the equal sign. You work on both sides separately, but don't ever combine them. So, here's their guidelines. Now, some of these I agree with. Some of them I have reservations on. I'll let you know. They say work with one side of the equation at a time. It's often better to work with the more complicated side first. Okay? That's fine, but I see no reason to just do one side and then go back and do the other side. If I see something that can be done on both sides as we go, as long as you don't cross the equal sign, you can work on both sides separately. So I don't strictly follow that. It is right. Pick the more complicated side to go with. If one side is as simple as you can get, don't mess with it. Okay? But always try to simplify. Okay? Look for opportunities to factor, like I just said, as long as it's all on one side. Add fractions all on one side, not across the equal sign. Square binomial, that would be okay, just on one side or the other. Create a monomial denominator. Any of those kinds of things that would be simplification of an expression, do on one side or the other. okay, but don't cross. Look for opportunities to use fundamental identities. Note which functions are in the final expression you want, in other words, the simple side. Sines and cosines pair up well, secants and tangents do, cotangents and cotangents do. Okay? Now here is where I'm going to add something a little more. Okay? No, you're in it, definitely, right? All right. All right. I'm going to expand on this a little bit, okay? If you have squares involved, that when you factored and did all the things you did up here, you still got squares, think Pythagorean identities. That's about the only thing you can do to deal with a square. Now, a little bit later in this chapter, we're going to get to some things that you can reduce squares. We're not there yet. So for right now, if you see the square, start thinking Pythagorean identities, and that's where they get the sines and cosines, secants and tangents, and cosecants and cotangents. They go together in Pythagorean identities. If the preceding guidelines do not help, then try converting all terms to sines and cosines. They put it off till late. I'll go to that one pretty early, okay, because it's usually easy. Now, if you got a bunch of squares in there, yeah, see if you can find the identities that will straighten those things out. But when you just got a lot of other mess, think of that. Okay, I go there a bit sooner than later. And then they say this, always try something. Even making a choice and doing something that doesn't get you anywhere, it might still give you insight in something that might work. My wife has turned me on to one of these telephone games called Wordscapes. I don't know if you've ever seen them. They give you a bunch of letters and you put as many words together as possible. That can get addictive. Always try something, you know, and sometimes in doing that, then I'll say, oh, no, I see, even though my choice was not a word, but I see the word now and I put those letters together. So always try something. Even making an attempt that leads to a dead end can provide insight. Okay. Verifying trigonometric identities is a useful process when you need to convert a trigonometric expression into a form that is more useful algebraically. So it'll feel like they've just come up with these weird combinations of sines, cosines, tangent, cotangent, all this kind of stuff just to give you something to do, like it's an exercise of futility. It's not. Sometimes in real life things are really complicated, and doing these identities get you into things that are simpler and more useful. Okay? So when you verify identity, you cannot assume the two sides are equal. That's what you're trying to verify. So I always start by putting a question mark there. And that helps remind me, don't ever cross the question mark, okay? Don't ever cross it. As a result, verifying identities, you cannot use operations of adding same quantities of each side or cross multiplication or anything else that you use for solving an equation. That's not what you're doing. You're trying to get this side to look like that side, not crossing the equal sign. All right, here's one fairly, I'm not going to say simple and straightforward, but it sort of is. Okay, it says verify this identity. Where would you begin? Any ideas? And by the way, there's several ways to approach these things. Several ways. Anyone got an idea? Just throw something up there, see if it sticks. Second? Okay, it sure looks sneakily like it might be in the Pythagorean theorem somewhere in, or Pythagorean identity involved. Secant squared, yeah, that's a dead giveaway. And I think that's a good idea, okay? So let's proceed that one. I'm going to come back and show you another one that may be better, may be worse. I'm not going to say one way or another, but let's try that anyway. I'll take it you're talking about the numerator here. What would that be, Pythagorean identity? It looks similar to 1. Is that exactly 1, or do we have to manipulate 1? What one does it look like? Here's the one that looks like to me. 1 plus tangent squared theta is equal to secant squared theta. Is that not one of them? Okay, and sure enough, if you subtract 1 from both sides, you get exactly this. So what would that be on top? Tangent squared theta over secant squared theta. And I always put the question mark there. Is that the same as sine squared theta? I don't know. Now, at this point, if you start messing around with more Pythagorean theorem, Pythagorean identities, you're just going to start running around a circle. You'll be like that little hamster on the treadwheel. You know, you just run and not get anywhere. So at this point, I go to, let's change everything to sines and cosines. So what's tangent squared in terms of sines and cosines? See, the right-hand side is already sines in terms of sines and cosines. We want the left hand. And here's done. All right, good deal. So what is tangent squared in terms of sines and cosines? Get to know them. They're going to be your friends. What is tangent in terms of sine and cosine? We did it, the vocabulary at the end of the last thing. Y'all were right on top of it. What is tangent? Sine over cosine. So I'm going to write this as a division. Is that okay? So I'm going to write this as a sine squared theta over cosine squared theta. And then I'm going to divide that by, and what is secant squared theta? Anybody? It's what? 1 over cosine. So that's 1 over cosine squared theta. So how do you divide fractional forms? Invert and multiply. So this will be sine squared theta over cosine squared theta times cosine squared theta over 1. And guess what? Ding, ding. You're left with sine squared theta, and that is exactly equals to sine squared theta. Done. You verified it. Notice you didn't ever cross the equal sign. Of course, the right-hand side is about as simple as you can get. Now, that was a way, and I think that's how the book would prefer you to do it. They love Pythagorean identities. Okay. But I'm going to make another suggestion to you. It's no better. It may be worse. But here's another possibility. Does anyone need this a little longer? Can I erase it? Okay. I'm going to show you another thing. Remember I just did the wrong thing. Okay, there. Remember they said, simplify your form. Okay? Well, this is, well, I just messed up. Okay. This could be written as secant squared theta over secant squared theta minus 1 over secant squared theta. Right? You just take that fraction. You got a monomial numerator. You just split that and put it under each of the monomial denominator. Put that under each of the numerators. That's a legal move in most states, right? Okay. And what is secant squared theta over secant squared theta? 1. And what is 1 over secant squared theta? Second? I think I thought I heard. Cosine squared theta. And what is 1 minus cosine squared theta? That's sine squared theta. That is equal to sine squared theta. I'm not even going to write it down. So there's another way you can do the same one. Like I said, sometimes many ways to get there. Okay? I know you're in here. I just got to get in the right class and then I'll find you. Okay. All right. Good. We're only missing Sarinthia, Ryan, Cody, Dimitri. Okay, so that's sine squared theta. So, my take on this, there may be several ways to get there. As long as you take right steps, that's fine. I don't care which way you go. See, what we did before, if you think about it, we started with the Pythagorean identity and then simplified the sines and cosines. what we did here was simplify the fraction that got us down to sines and cosines just by, that was easy, and that we got the sine and cosine, and then we had a Pythagorean identity. So basically we used the same steps, just change the order ever so slightly. Okay. There was example 1. Let's see how they did it. I gave you a couple ways to see if, I think they did one of those 2 ways. And oh no. Boy, did they ever do it complicatedly, okay? They said start with the left-hand side, that's fine, because it's more complicated, that's fine, that's correct. But then they started with this, the one that I wrote down, and put it here, then did the -1, and then got to, we did it in one step, or we did a little scratch work out there and found out that was exactly tangent squared. So again, they just took an extra complication here, but it still works, okay? That gave us exactly what we got, tangent squared over secant squared. And then, I wouldn't have done it this way either, but it's fine. Notice that 1 over secant squared is cosine squared, so you got tangent squared. And then noticing that tangent squared is sine squared over cosine squared. Why don't you do it all at once, changing both of them to sine and cosine? Then you can cancel that out, and you get sine squared equal to sine squared. Notice that you verify the identity by starting with the left-hand side, the more complicated side, using the fundamental trigonometric identities and regular mathematical algebraic operations to simplify it and obtain the right-hand side. Now, this whole section, and they do one example. That's all. That's all, folks. So we're going to need to do a few more. Okay? So let's start with example 2. Okay? I think we're going to be using this slide to death. We may wear it out. Let's see what happens. Verify this identity. 2 times secant squared theta, no, alpha. It doesn't matter what your argument is. That's sort of a dummy variable anyway, but I'm going to try to do it the same as the book. 2 secant squared alpha, and the question is that equal to 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. Okay. Now, how would you begin?
Could we add the 2 fractions?
Second?
Could we add the 2 fractions?
Okay, excellent idea. You got fractional forms over there, which are always a bit more complicated than things just multiplied and raised to powers. So let's add those 2 together and see if we can get anything to simplify. Now, before you can add fractional forms, what do you need? Common denominator. Now, what would be the common denominator between those 2 denominators? You had 1
plus.
second?
1 plus sine.
Okay. Yeah, you would have to, okay. If you were adding the 2 fractions together, 1/2 plus 1/3, what would be the common denominator? 1/2 plus 1/3. Second? 1/6. How did you get that? You multiplied them together, right? Because there were no common factors, just multiply them together. Well, there's no common factors here either, so we're going to multiply them together. So the common denominator is going to be the product of these 2. So I guess I'll take another step down here and do it. So down here we have a 1 minus sine alpha. Over here we have a 1 plus sine alpha. Okay? Now the common denominator is going to be the product of these 2. So you're going to have to multiply this one by 1 plus sine alpha. And you're going to have to multiply this one by 1 minus sine alpha. But you can't just multiply the denominator by that. If you're multiplying, you got to multiply the numerator by it as well. So here it's going to be 1 plus sine alpha, and over here it's going to be 1 minus sine alpha. Okay, I didn't write down my 1s because I'm just multiplying this by 1. Because you see, This over that is 1. You wind up with the same thing here. This over that is 1. You wind up with the same thing there. So that's it. Now what do we do? Since we found common denominators, what do we do? Not multiply. Oh, I see what you say. You could, and maybe we will, but for now, I'm going to leave them alone and add the numerators. Once you have common denominators, like if you have 3, 6, and 2, 6, you keep the 6 and add the numerator. 3 plus 2 is 5. That gives you 5, 6. Well, you keep the denominator and add the numerators. Okay, so this would be 1 minus sine alpha. And it would be a smart move to go on and multiply them, but I don't want you to focus on that yet. Let's just focus on this. Okay, you can do more than one thing at once, but I'm sort of simple-minded. So add the numerators. So you get 1 plus sine alpha plus 1 minus sine alpha. What do you wind up with in your numerator then, besides all this extraneous writing? What happens there? The signs add to 0, and you wind up with 2 in the numerator. That's all. Over. Now, I'm going to take Jake's suggestion, which I probably should have taken earlier. Let's multiply those denominators together, those factors in the denominator together. And what do you get? Anybody? 1 minus sine squared alpha. Okay. And what is 1 minus sine squared alpha? That's 2 over cosine squared alpha. And what is 1 over cosine squared alpha? That would be 2 secant squared theta. And that is exactly what your left-hand side was. Okay? Now, even though my tendency is to go, you get everything in terms of sines and cosines, in this case, no, let's simplify that right-hand side because it's adding fractional forms. That's a fairly complicated algebraic situation. So let's simplify that. And once you did, and notice that that denominator is indeed Pythagorean identity, you can then write it that way. And you got it. Make sense? They're fun, aren't they? Okay, say it like you mean it now. Okay. All right. Any questions on that? That was example 2. And I think they did it pretty much the same way y'all chose to do it. Okay. Let's go to example 3. Does anyone need this a little longer? Yay or nay? No? Okay. All right. Let's do example 3. Verify this identity. Tangent squared theta plus 1 tangent squared x plus 1. They just keep changing the variables on me just to throw me off, and that's easy to do, times cosine squared x minus 1. Is that equal to negative tangent squared x? Where would you begin? What would you suggest we do first? Okay, looks like there's pretty close to some Pythagorean identities right here. What is tangent squared theta plus 1? Tangent squared x plus 1? Anybody? That's secant squared x. Okay, now this one's not quite exactly a Pythagorean identity, but it's awfully close. What is that? Is what? Not quite. Close to sine squared, but not quite. What's wrong with it? sine squared theta is equal to 1 minus cosine squared theta. But this is cosine squared theta minus 1. So what can you do to make those, to reconcile that? Negate both sides, right? And now what do you have? Cosine squared theta minus 1 is minus sine squared theta, right? So this is minus sine squared theta. Does everybody see that? Or x, not theta, x. I put thetas up above. They were all x's. Or you could have thetas there. I don't care what you have there, but our problem was x's. And my problem is reading things properly. Okay. So, now what would you do? Any ideas? Anybody? Okay. Let's not do any more Pythagorean identities. That's where you get on the treadmill and just go round and round and round in circles. So what might you try now? What's my always favorite fallback? Get everything in terms of sines and cosines. This is already in terms of sines, so let's get this in terms of sines and cosines. What's that? Say again? 1 over what? Cosine squared theta. Exactly. And then what do you have? Oh, they're x's, not thetas. Goodness gracious. Jake, that's your fault. You keep making me say theta, you know? Huh?
I just write them on the stage.
All right. And guess what? Sine squared theta over cosine squared theta is tangent squared theta, and you got the minus sign, so this is indeed. Now you could either, on this side, make this minus tangent squared theta, x, Jake, you did it again, okay, or make this one, bring this down to be minus sine, down here, minus sine squared theta, x over cosine squared x, okay. And then you got, see, if you bring down both sides, you get there a step earlier, rather than having to take all the way back around. But it doesn't matter, whichever way you want to do it. But you see, those are indeed the same. Both sides of the equation is sine squared, minus sine squared over cosine squared, or minus tangent squared. Make sense? They are fun, aren't they? It's like a puzzle. Maybe not quite as much fun as Wordscape, but close. Okay, never mind. All right. That was example 3. Y'all ready for example 4 yet, or still working on that? Ready? Can I move? Okay. Example 4. There are 2 of these. Here's one. Tangent x cosecant x they say is equal to secant x. The question isn't. What would be your approach on this one? I'd say get everything in terms of sines and cosines. What is tangent in terms of sines and cosine? Sine x over cosine x. Okay? What is cosecant x in terms of sines and cosine? 1 over sine x. Okay? Now, frankly, I would do this. I would write this in terms of sines and cosine too. What is secant x in terms of sines and cosine? 1 over cosine x. Okay? And here your sines divide away, and you get 1 over cosine x equal 1 over cosine x. Done. Right there. You could write one more line and make them back to secants if you wanted to. I don't care. But you showed that these are indeed the same for all values of x. That makes sense. Okay. So that's the first one. Okay. The A. Let's do the B. They say that tangent x plus cotangent x is equal to secant x cosecant x. Okay? What would be your approach on this one? Anybody? How would you proceed? I'd say get everything in terms of sines and cosines together. That's my favorite anyway. So what is tangent x in terms of sines and cosine? Is sine x over cosine x plus, and what's cotangent x in terms of sines and cosines? Cosine x over sine x. Okay? The question is this equal to, and what's secant x in terms of sines and cosines? 1 over what? You probably said it, I just don't hear well. 1 over cosine x. Okay? And what's cosecant x in terms of sines and cosine? 1 over sine x. Okay. Now, the right-hand side has a denominator that's sine times cosine. And this has sine and cosine in the denominator but added, but to add fractional forms, what were you going to do? Common denominator. And what would that be? The product of sine and cosine. So that at least is going to get us the same product. So what have we got to do to the first one to make this a product of sine times cosine? Multiply it by sine. But if you multiply the denominator by sine, what have you got to do? Multiply the numerator by sine as well, which will make it sine squared. Now to make that second fraction a sine times cosine, what would you have to multiply the denominator by? Cosine squared, cosine x. But if you multiply the denominator by that, you have to multiply the numerator by that as well, and that becomes cosine squared x, right? Oh, I meant to tell you, it just caught my attention. Sorry to break your train of thought here. Dr. Bryant, our physics instructor, brought this in to me yesterday. It's a 2019 research experience for undergraduates. It's basically most of the summer, okay? I believe it's a 10-week program, whatever that turns out being. Pretty close to it anyway. Experimental and computational materials research. The support is $5,000 for a 10-week appointment. Y'all going to be making that kind of money this summer? Maybe so. If so, stay with it. But if you're interested, additional support for travel, housing, and other expenses. So they may house you, maybe even feed you, and provide at least some travel for it. And this, by the way, is at UAB, so it's not very far anyway. And there's all these different research experiences, electronic materials, biophysics and biomaterials, nanomaterials, lasers and optical materials, planetary materials, biomedical research, computational materials research, biosensors, and more. Okay? It's at UAB. The problem is the deadline is, no, I saw it on there somewhere. Oh, here it is, March 15th, which is, I believe, Friday. So if you want to do this, get hopping, okay? We are encouraged to apply early. We not have much time to apply early, but apply as soon as you can. And participants will check into the dorms, see they house you, and I think in the dorms they feed you. So not a bad deal, and they pay you $5,000 on top of that. And they provide travel for wherever your home is, to UAB wants to get there and wants to leave. You can go back and forth as many times as you want, but they pay for only one. Wants to get you there and wants to leave. So here's, I think, all the details. And so look into it if you're at all interested in any of those areas. They sound great, okay? And it's called the Research Experience for Undergraduate, REU. I'm pretty sure it's National Science Foundation paid for it, so it's a good deal, a very good deal. All right, let's get back to this. So what do we have here? We have common denominator, sine squared times cosine squared, same as we have over there. Okay, so we'll keep the denominator on this side, sine x times cosine x. And what does our numerator become? Keep the denominator, add the numerators. And what's sine squared? What's cosine squared? 1. So you just have shown these two are indeed equal to each other. Done. See? Pretty good, huh? Any questions? Make sense? All right. So that was example. Oh, and they go around. Yeah. All right. And by the way, every one of these examples has a checkpoint. Please go back and do the checkpoints as soon as you can after class, just to refresh and embed the concepts in your mind. Right now you're spectating. Hopefully you're thinking through and participating, but in many ways it's spectating. Then you're doing it. It becomes yours. Now, going back to something, and they have a little blurb here, and why they didn't have this on the slideshow, I don't know. But I'm going to deal with their blurb. I should have asked if anyone needed that a little longer, but y'all all seem to be looking. What if you have something like this? 1 over 1 minus cosine x, they call it here. Okay. And it's something you have to deal with, and there doesn't seem to be much of another way to deal with it. What's the technique for modifying that? Any ideas? It's something you've done throughout your algebra careers, I bet. And you may not have always called it this, but it is the same concept. If that was a radical down there, what would you be tempted to do? If it's in the denominator. Yeah. Okay, yeah. You multiply by its, you remember what they call that? Conjugate. Okay? But you've done this in other contexts as well. Even something that looks like this. What would be the conjugate of this? 1 plus cosine x. But of course, if you multiply by that, you'd have to multiply the numerator by this as well. Okay, so I've done it. Now, in any context, that's the conjugate. You have the same first thing, same last thing, but you change the signs. Okay, one's with a minus, change it to plus. If it's a plus, change it to a minus. Now, what happens when you multiply those two together? What do you get? Anybody? You want to follow it? Second?
1 plus cosine squared.
1 what?
Plus cosine squared.
I don't think so. 1 minus cosine squared x. And here's why. Why don't you follow it? 1 times 1 is 1. That's where that comes from. Then the outers are positive cosine x minus cosine x adds to 0. And then you have a minus cosine squared x. Okay? Doesn't look like a very happy face, but it's sort of a happy face there. Okay. Well, what is 1 minus cosine squared? Sine squared. Exactly. So, especially in trigonomic senses, if you have a binomial in the denominator, especially if one's involved with a sum of your trig functions, okay, try multiplying by the conjugate. It may take you down a dead end, fine, you can try something else, but at least you can simplify that. You see, you go from being a binomial in the denominator, which you can't do a lot with, this becomes a monomial. And you can do lots with a monomial in the denominator you can't do with a binomial in there. So that's the advantage of multiplying by the conjugate. Sometimes. Other times it may or may not work. Okay? Now, here is another situation. Okay, well, it may be that you wind up with this, something like this in a numerator, and you can't think of anything else to do. Try that too. It might help. It might help. It may not, but I bet you in the next problem it might. So let's do the next example. Okay? Verify this identity. Secant x plus tangent x. Okay? They claim that's equal to cosine x over 1 minus sine x. Okay? Now, this is another one of those situations, at least in my mind. Sure, the right-hand side is a bit more complicated, mostly because it has a denominator. It's a fractional form. The left-hand side isn't. But what's more, it has a binomial in the denominator, which is hard to mess with. And the left-hand side, of course, has no denominators. But, on the other hand, the right-hand side is already in terms of sines and cosine. The left-hand side is not. So, in my mind, let's work on both sides at the same time. Not crossing the equal sign, but just work on them separately. What does the left-hand side become? What would you do with it to simplify it? Sines and cosines. So what would that be? 1 over cosine x plus sine x over cosine x. Okay? Ha! The left-hand side's already looking better to me. But what we don't know is what we're going to do with the right-hand side. So what would be your suggestion, especially in light of what we just talked about? Multiply by its conjugate, which would be 1 plus sine x. Okay? Now, there's a lot of promise in making the denominator simpler, but that's actually going to make the numerator more complicated, because you have to also multiply it by 1 plus sine x, because you have to do things fairly. Okay. So, what does this become then? And if I were you, I would leave that in factored form in the numerator. Maybe later we'll want to multiply, but at least for now, let's leave it alone. This would be cosine x times 1 plus sine x. Leave that numerator alone. What's the denominator become? Anybody? Okay, you jumped right to it. Yeah, it first becomes 1 minus sine squared x, and that is exactly cosine squared x. All right. Now, I hope you see things coming together pretty nicely here. On the left-hand side, you have your least common denominator, which is cosine x, and your numerator becomes 1 plus sine x. Oh man, that's looking pretty good, isn't it? Over here on the right-hand side, you can divide out one of your cosines, right? And what do you have? Exactly the left-hand side. 1 plus sine x over cosine x. Yep. No more question about it. That's definitely an identity. Make sense? Now, you don't have to do it this way. This is just my little favorite way of doing it. There's lots of ways to get there. As long as you take the right steps in every way, you should be able to come up with the right answer. Some right steps may get you nowhere, but you should still be able to get it. All right, so that was example 5. And by the way, it says see larsonprecalculus.com for an interactive version of that type of example. And reminding you, too, the checkpoints are also all found at larsonprecalculus.com. Audio, video solutions are there. All right. Any questions? Ready for example 6. Now, don't let me get too carried away. I always lose track of time in this class because it's so much fun. Okay. We go till 11:15, right? All right. Well, since I didn't set my clock back, we got more than an hour to go. All right. Good. No, ahead or whatever. Okay. So, let's clear that one and go to the next. And this is example 6 now, right? This one says that cosine squared theta, going back to my favorite theta, over 1 plus cosecant theta I don't know if this is equal or not, 1 minus sine theta over sine theta. What's your first impression when you see that problem? What goes through your mind to begin with? Anything? Besides, oh joy, another identity to work on. Okay, I know that's going through there, but anything beyond that? Okay.
We could use a Pythagorean identity on the cotangent squared theta.
Okay, he says a Pythagorean identity on the cotangent squared theta. That sounds like it might be a pretty good idea because cotangents and cosecants, they relate to each other there. So that's a pretty good idea. So what would that be? What is your
That'd be
cosecant squared theta minus 1. Okay? Everybody agree with that? Very good insight there. And that's over 1 plus cosecant theta. It gets you into the same terms there, and over here you got the same terms there. Now, I don't know if you want to mess with anything there or not. It's up to you. Maybe or maybe not. What you think? Leave it alone for now? Or mess with something?
We can change it to...
You what?
Change it to 1 over...
Yes. Okay, that's what I was thinking. Do 1 over sine theta minus sine theta over sine theta is 1. I think that's a little simpler, personally. But then, okay, we'll get to that later. Okay, let's continue on the left. What might you do next? Oh, let's factor. Why don't we do that? Okay, and this will be what? Cosecant theta plus 1 times cosecant theta minus 1. Okay, over. And you can write, because addition is commutative, you can write this as cosecant theta plus 1. You don't have to write it. It doesn't matter the order. And now you see, ping, ping, with sound effects, you lost a factor there, which is a very nice thing to do. Now, what do you notice? What is 1 over sine theta? Cosecant theta minus 1. And what do we have here? Cosecant theta minus 1. Oh my goodness, look at that. Worked nicely, didn't it? Now, you didn't have to do that other thing over there, but you take a couple more steps to get those worked. But you see, by sort of simplifying both sides as you go, you might wind up with the same simplification, which I think you do. Maybe not every time, but quite often. Make sense? Good problem. Okay. And they suggested on this one you work with each side separately also. And they did it the same way we did. They just split the order. I don't know. There's a checkpoint there and the audio video solution at the checkpoint is there too. Now, do we have time for one more? I think so. Let's see if we can get this one done. Example 7. Any questions before I erase this? Everybody got it? Okay. Now, verify. Oh, there's 2 of them here. Here's one. Tangent to the 4th x. Supposedly that's equal to tangent squared x, secant squared x, minus tangent squared x. What would be your suggestion here?
Get everything in the sines and cosines.
Second?
Get everything in the sines and cosines.
Okay. A lot of times I like that. This one, I think you'll be better off. See, that's going to introduce some fractional forms. This so far isn't in fractions. Let's see if we can just deal algebraically with the right-hand side first and see what we come up with. What would be the first thing on the right-hand side that you would do? Second? I thought I heard someone say something. Actually, almost sounded right, but I just couldn't make it out. What would you do first? Huh?
I'd rather do something on the left side.
You start with the left side. Oh, shame on you. Okay, what would you do there?
I'd change it to tangent squared x times tangent squared x.
Okay, let's do that then. Tangent squared x times tangent squared x. This certainly will work if you go in the right direction here. I think you will. And then what?
Use the Pythagorean identity.
On one of them?
On one of them.
Yeah. Okay, so let's do a tangent squared x. And what's the Pythagorean identity there?
We make it secant squared x minus 1.
Secant squared x minus 1. Very good thought. Okay. I would also do something on the right-hand side, which would be what? Factor out a tangent squared x here. And what leaves you with a secant squared x minus 1. Yes, and now they're the same. Good insight to do that. I was just going to go this and then get this. See, that is the Pythagorean identity to that. And then we have tangent squared x. So either way you do it, both ways work quite nicely. Good insight. You got the same way, perfectly fine. Do we have time for the last one? I think we do. That one went so well, and I think it's fairly similar. Cosecant 4th, is it x again? I think so, times cotangent x supposedly is equal to cosecant squared x times cotangent x plus cotangent cubed x. Where did that come from? Which way would you proceed with this? Any ideas? I'll accept all ideas. May reject some, but I'll accept them to begin with. What might you do? Anybody?
Do something on the left side again.
Okay, he's going to start with the left side again, so what are you going to do?
Change it to cosecant squared x.
Cosecant squared x times cosecant squared x times cotangent x. Okay? You're just going to work with that side, going to do anything to the right.
You can factor out a cotangent.
I think that's a good idea too. Here we have a cosecant squared x, and here we're going to factor out a cotangent x. And what do we have left?
Make it 1 plus
Cotangent squared x. Okay, and now what?
Change one of the cosecant squared x on the left side to 1 plus cotangent.
Okay, you certainly can do that. So let's keep the first one, cosecant squared x. Change the second one to a 1 plus cotangent squared x. Is that what you said? And then you still have a cotangent x here. And sure enough, that is exactly equal to the right-hand side. The order is different, but multiplication is also commutative and associative, so you can do that. Perfect. Pretty nice, huh? All right, that ends the section. There's a couple checkpoints there. I'd certainly do those. Do we have time to do the vocabulary? Or not?
3 minutes.
3 minutes, I think we do. An equation that is true for all real values in the domain of the variable is an identity. Perfect. Number 2, an equation that is true for only some values in the domain of the variable is a blank blank. Conditional equation. Excellent. 3, 1 over cotangent u is, quickly, tangent u. Cosine u over sine u is cotangent u. Cosine of pi halves minus u is sine of u. 1 plus blank is cosecant squared u. Cotangent squared u. Cosecant of negative u is negative cosecant of u because it's an odd function because it's reciprocal of sine and sine is odd. And secant of negative u is secant u because it's the reciprocal of cosine, which is an even function. Then homework exercises include any of the odds, 9 through 17. They're all at Calc Chat, 9's at Calc View. Do any of the odds, 19 to 23, they're all at Calc Chat, 21's at Calc View. Any of the odds 25 to 29, they're all at Calc Chat, 27's at Calc View. Any of the odds 31 to 35, they're all at Calc Chat, 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat, 41's at Calc View. You can do 43 if you'd like. It's one of those that they've made an error on purpose. They ask you to find it. Any of the odds, and that should be at Calc Chat also. 45 to 49, they're all at Calc Chat. 51 or 53, they're both at Calc Chat. 51's at Calc View. 55's at Calc Chat. 57 or 59, they're both at Calc Chat. 57's at Calc View. 61's a rate of change problem. It should be at Calc Chat. 63 is a true, and 65 are true false. They should both be at Calc Chat. And you can think about doing 67 or 69 if you choose. Okay? Good deal. All right. Making good progress in Chapter 5. We will keep going and pick up then on Thursday. Okay. Good deal. Any questions? All right. Huh? Okay. Good deal. Thank you. Appreciate it.
Got that letter written yet?
Okay. I can't swear I'll get it done Wednesday, but I'm going to try to. I've got they changed the summer schedule drastically this summer. So that's what I spent basically my 2 hours and my 2 hours and 15 minutes yesterday, just almost completely immersed in the summer schedule. That's done. I'm almost caught up with my grading, and I think I'm going to have some time in the morning. Don't know for certain, but I think I will. But
do you have any office hours today, by any chance?
Not really much. What do you need?
I was going to talk to you about it. Listening to change my major.
Oh, okay. See, I've got 15 minutes between these two classes. Then I've got 30 minutes between the next two classes, and the last class goes until 5:45. So after 5:45, I'll be free.
I'll be gone by
Yeah.
then.
you know any? Will you be Friday?
Friday, I'll be on the Birmingham campus, but I've got that eye appointment early, so I'm thinking I'll be there between 10 and 12.
Thursday.
Thursday is just like today. Okay, I have 30 minutes at the beginning.
Mm-hmm.
You know that 8 to 8:30. I'm in the office. This morning I was setting up a lab, but maybe doing the same on Thursday. But I have very little office hours except right at the end of the day. Tomorrow I've got from 8 to 10.
8 to 10, I'll be in class.
Yeah, I'll be in class.
On the other campus.
Okay. Friday on Birmingham late, is that not good?
I usually work.
Oh, okay. Monday again, 8 to 10 and 3:45 to 6. So that might be best.
Yeah. Monday. What'd you say Monday?
8 to 10, but you're in class probably, and then 3:45 to 6.
I don't know if I'll work Monday or not. When I do work, it's usually 4 to 10. So.
Yeah, so that's going to eat up much of that time. Well, anyone can sign a form. Just do the form. If all it is a signature, you can catch me anytime I can sign it.
I was also thinking, since I'm going to change my major, I've been really falling behind in that chemistry class, and I don't think I can make myself back. I was thinking of maybe dropping it so it wouldn't hurt my GPA.
Right.
But I want to know, do you know how that will affect my scholarship and all that?
No, I don't have the answer to that. You have to ask the scholarship people.
Isn't it
Usually, withdrawals don't hurt you, but you have to check with them to see the details.
Because I think it's like if you withdraw after a certain date, it shouldn't hurt you.
Right. Yeah, there is what they call the
I know you can
60% completion date, which is coming up really soon. Check the academic calendar. You'll see it on there. 60% completion date for full-time courses.
Yeah.
It's sometime this month.
Because I am full-time, and I don't know what will happen if I drop it.
Yeah, no, that you'll have to ask them that. Yeah.
Okay, thanks for that.
All righty.
So sometime next week, maybe?
Yeah, and if it's just to sign a paper, I can do it this week too. Anytime you can catch it. Okay, right. That's it.